Okay, financial modeling guys, we are now going to talk about, ARq models and also moving averages, PQ models. Okay. So what is it all about, So it really looks scary, but it's actually very not scary. Okay. So let's recall that AR1, right, has the following equation. So RT equals to alpha plus gamma times RT minus 1 plus epsilon. Okay. Now, this tells you, right, that in order to predict RT, you need basically just to know RT minus 1. Now, what people did, they said, you know what? It's not good enough. Maybe there is, maybe something that happened 2 days or 3 days or 4 days ago, right, also have some bearing on what is happening now. How can we incorporate it into our model? Well, it's actually easy peasy. We will say that RT equals now alpha plus gamma 1, right, times RT minus Q plus gamma 2 times RT minus Q minus 1 plus yada 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 gamma Q times RT minus Q plus epsilon T. Okay? So in this particular case, what you're having, right, that the expected value of RT is actually going to be dependent not just on what happened yesterday, but what happened, let's say, 100 days ago, right? So if Q equals, let's say, 3, right, how the model is going to look like? RT equals to alpha plus gamma 1 times RT minus 3 plus gamma 2 times RT minus 2 plus gamma 3 times RT minus 1 plus epsilon T. Okay? So that's kind of going to be, right, a toy model for a, for a predictor that is going to be, let's say, 3 days from now. Now, how one, right, as we saw, is actually somewhat difficult to predict. When it comes more and more and more, it's becoming even more impossible, right? So for example, let me just give you an example how I'm going to calculate the expected value of RT. So the expected value of RT, right, equals to what? Now I will assume that all of them have the same expected value. So I'm having alpha plus, and now I have gamma 1 plus yada 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 gamma Q, right, times the expected value of RT, and this guy is 0. So I'm going to get the expected value of RT, right, equals to alpha divided by 1 minus the sum of gamma I, right? So if I have this 3, right, I'm going to get that the expected value of RT equals to alpha divided by 1 minus gamma 1 plus gamma 2 plus gamma 3. Here's what happens. You see, we talked about stationarity, right? In order for us to be stationary, gamma 1 plus gamma 2 plus gamma 3 must be less than 1, right? So now, not only we need to estimate those guys, we kind of have all kinds of crazy constraints. For example, in this model, right, we're having constraints that gamma 1 plus gamma 2 plus gamma 3 must be less than 1. Okay? So, it's becoming more and more and more unwieldy the more things you're getting in. Now, how to estimate something like that, right? So for this, it's actually more or less reasonable what you do. I mean, and it's you look on the changes, you subtract, you basically can, what you can do, for example, you can run, you can subtract, let's say, RT minus 1 from both sides, right? And then what you're doing is then you're getting kind of, let's say, assuming you're getting a stationary process, you're kind of running a regression of RT minus 1 versus RT minus Q minus RT minus 1, RT minus Q minus 1 minus RT minus 1, etc., etc., etc. So you have gamma 1, gamma 2, and gamma 3, and then, if you don't have a better statistics like the Dickey-Fuller statistic in this case, you're just using T-stat in order to kind of test whether these guys, are zeros or not. I mean, that's the only way for you guys to do it. I mean, it's really, it's really becoming unwieldy. Now, why do we have such models? Well, that's a good question. Okay, we have such models because if we believe that if we believe that R is mean reverting, right? So if it goes up, it comes down. This kind of a model, right, will predict it because you see that it's kind of depending on what happened before. Okay, now, well, this is not enough, right? Because here we have only one error term, right? So this error term doesn't depend on anything, right? But now people, it's not enough for them, so they have something called maturity, something like that. And here, right, they're actually going to add some error terms which are independent of the final error term. So the process can be something like that. RT equals to epsilon 1, like say alpha 1 epsilon 1, alpha 2 epsilon 2, yada 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 yada, alpha q epsilon q, alpha q epsilon q plus, and now you are going to put the r's, it's going to be gamma 1 RT minus q p plus gamma 2 plus RT minus P minus 1, yada, 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 plus gamma P times RT minus 1. Okay? So this is kind of called moving averages. Why does it called moving averages? Because then you model R, right, as some sort of a moving average where your moving averages is basically not RTs themselves, not RTs, but also, kind of errors of RT. So, if, for example, you had, let's say, R1 plus epsilon 1, for the first day. Then you had R2 plus epsilon 2 for the second day. And let's say then you have R3 plus epsilon 3 for the third day. Let's say that, these are your distributions. What is going to be the distribution of the average, right? The distribution of the average is going to be R1 plus R2 plus R3 divided by 3. Right? This is going to be kind of, one piece of the puzzle, but then you have to add the error. So it's epsilon 1 plus epsilon 2 plus epsilon 3, and all these divided by 3, right? So what you have here, you have like a moving average thing where you are getting some, some expected value, but you actually look on the actual values because R1 plus epsilon 1, R2 epsilon 2, and R3 epsilon 3, they're actual values, right? The R1 is your expected value, but then you add an error. So you kind of look on the actual errors, right? And you look on the moving average of the actual error. Now, why is it interesting to people? Here's one motivation. Technical trading. Okay. If you have a technical trading where something, where you are basically looking on a moving averages, right? Let's say that this guy is here, and if it's a moving average, you buy, and if it's not a moving average, you sell, right? Then you're kind of entering into this kind of realm, into this kind of, regressions and this kind of projections, because then your RT, right, will depend on the moving average. So technical trading will say, a rule will say buy if bigger than moving average, for a week or something, right? Something like that, right? So then you are basically having a model like that, right? And then your R7 will depend, let's say, on R1, R2, R3, R4, R5, R6, plus their errors, right? And then you're entering into something like that. Now here, right, your gammas are 1/3. But you can come up with a much more difficult rules where you can say, oh my God, I want basically half of that, right? I don't want like a regular moving average. I want like half of that, third of that, and quarter of that, right? Like a portfolio, okay? So if your value is bigger than a certain portfolio of returns which was created before, you're going to buy. If it's less, you're going to sell, okay? And these kind of rules, right, are actually prevalent. Whether or not they're working is a different story, but for commodities, for example, they're actually very, very popular, okay? You have, when you go to commodities, you always look on bands, you always look on, on this kind of technical rules. And these kind of technical rules, if you want to model those processes, right, you have to use something like that. So it's not just the values themselves, right? It's a mix of a value and errors which depend on the day which they were created. It's actually a very, very, very complicated thing to try and estimate. Okay? So that was it for the major ARq, MAPQ, and ARq. And hope that this video at least gives you some motivation of how people on the street think about those things. Now, whether or not it works or not, it's a different story, right? We're now looking on the theory. We're not looking on the, on the practical implementation. All right? Thank you very much, and have a great day.